This section is all about logarithms. We're going to look at the introduction and the properties of logarithms and just kind of a general overview of logarithms. So first off, let's look at why do we use logarithms? Well, a lot of times in science and we deal with big numbers and groupings of numbers, we deal with such a large range of numbers that it's hard to put those numbers onto a number line and look at them in the same scale. So we use what's called a logarithmic scale. And here's how it works. If you look at the intensities, you have the relative intensity and the decibels here. This is of sound. And if you look, we got 10 to the 0, and then each one goes up by a power. You got 10 to some power. So 10 to the 0 is to be 10 to the first, 10 squared, 10 to the third, 10 to the fourth, and so on, and on and on. So if you look, 10 to the 0 is 1. 10 squared is 100. So we went up 2 spaces, but we went up 100. Okay, so if I were to continue this in a linear matter, this would be 200, but it's not. This is actually 10,000. And all the way up until you have 10 to the 12th, which is a really large number. So we can't represent all these numbers from 1 all the way up to 10 to the 12th on a number line that we've talked about before because, well, I'm going to show you why, but because the numbers get too jumbled and it doesn't accurately represent it. So we represent it with logarithms. This number, this exponent right here, if you notice, they correlate, and those are the logarithms. So let's look at this on a number line. If I were to make a number line from 0 to 10 to the 12th, which is what I would have to do to represent all these numbers, and I would say, okay, well, where's 10 to the 0? Well, 10 to the 0 is 1. So we put that right there. This is 10 to the 12th. This is 1 and 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is a large number, to say the least. What is that? Million, billion, trillion, quadrillion? That's 1 quadrillion. And here we have 1. So then our next one would be 100. Well, where is 100 in reference to 1 quadrillion? Well, it's really close to 1, almost right on top of 1. And you'd say, well, where's 10,000? Well, 10,000 is still really close to 1. And then even 1 million would still be really close to 1. It'd be like right here. So it's really hard to represent this huge range of numbers on a linear scale, so we use logarithms. And that's just kind of gee whiz information, so you can kind of see where it comes from. Now we're going to look at the definition of a logarithm. Where does the actual function come from? So we've talked about exponentials. That was the last lesson. Here's our exponential graph. The blue is our exponential graph, y equals 2 to the x. And logarithms are the inverse of exponential functions. So as you can see here, I got y equals 2 to the x. I flipped the x and the y. That's our steps. All right, so I got negative 3 1/8, so it becomes 1/8 negative 3. And you look at the table, all the numbers are flipped. And on our graph, it's flipped across the line y equals x. So they are inverses. But if I were to graph this in my calculator, I couldn't graph x equals 2 to the y. I need to get that y by itself. Well, in order to do that, I use the definition of a logarithm. So these parts match up. The bases will always be the same. If the base of the logarithm is 2, the base of the exponent is going to be 2. What I'm taking the log of is what I'm equal to. And what I'm equal to in the logarithm is my exponent. And I need you to keep this in mind, so when we go to work these problems, you can see where this comes from. This is something you have to become very familiar with, because we'll be converting back and forth, and in order to solve logarithms and solve exponentials, this is the easiest way to do it. Remember what I said, logarithms and exponentials are inverses. Logarithms and exponentials are inverses of each other. You can see that right here by this graph. So let's solve a few examples. First, we're going to write what we're given in logarithmic form. Well, keep in mind that we're going to be using this. If it would have showed up in the correct spot. We're going to be using this definition of a logarithm. Oh, that's not the right spot. Let's try that again. move it up, not down. I don't know why I posted it at the bottom of the page, but yeah, we'll work with it. All right, so we're trying to find what these exponential equations are written in logarithmic form. Okay, so we're given this form right here, and we're trying to get it back to look like a logarithm. So we just have to match up our numbers. So if you look, our green is our exponent, so let's highlight that, green. Okay, our yellow is what we're taking the log of, which in this case is what we're equal to. Okay, and then lastly, our base is 5. Our base will always be the same. So when we rewrite this, we just match up the colors. So log base 5 of 625 equals 4. So you're just using the definition of a logarithm to rewrite this. So I'm going to do the same thing with this one. I'm going to do a little bit faster. Log base 2, because my base is the same. What I'm equal to becomes what I'm taking the log of, and my exponent becomes what I'm equal to. And we're going to convert again. We're given exponential form, and we're going to convert it to logarithm form. This is actually easier because you can say, okay, this number right here, this base, raised to this exponent equals this. Okay, so raised to equals. And that's all. This, I think it's easier to go from logs to exponentials. So here we have 13 squared equals 169, which is true. 13 squared does equal 169. Next we have 4 raised to the third power equals 64. So 4 raised to the third power equals 64. That's the definition of a logarithm. 4 cubed does in fact equal 64. Alright, so let's use these properties of logarithms and the definition of a logarithm to solve equations. So here we have 3 choices for a variable. Our variable can be the base, our variable can be what we're taking the log of, or our variable can be what we're equal to. In each scenario, we still use the definition of a logarithm to solve. So first off, we look at, again, b raised to this power equals that. So b squared equals 121. So what number squared would equal 121? Well, that's 11. And we don't look at the negative version when we talk about logs. Negative base, that is. So next we look at this 6 raised to the third power equals x. So 6 raised to the third power equals x. Well, what is 6 to the third power? In your calculator in your head, that's 216, I think, equals x. So x equals 216. We solve for the variable. Lastly, we got 5 raised to the x power equals 10. So 5 to the x power equals 10. Now we've seen problems like this before, and we had to get the bases the same, and that means the exponents are equal, but we can't do that here. We can't actually get a base of 5 and 10. We can't get a whole number base that's the same. Well, the good news is, when you were given a problem like this before, you might not know how to solve it. Well, now if you're given a problem like this, you can rewrite it as a log, which is what we were given, and you can just plug that straight into your calculator. So calculator, here it is, and we're just going to put this straight in. So I can't actually do it like your calculator can, so it's going to look a little different. But if you put log base 5 of 10 in your calculator, this is how you do it on your calculator. I can't show you. I forgot this calculator's a piece of crap. If you go to math, alpha, math. Math, alpha, math. So math, alpha, math. It's going to bring up something that looks like this. It'll be log with a box and then another box. And you just put your numbers in. So you'd put in 5 into this box, you put in 10 into the other box, 5, 10, and you would get whatever that is. So you put this in your calculator, you should get 1.4 .431, roughly somewhere around there. So that's how you do on your calculator. So previously, if you were given a problem like this, you couldn't solve it. Now you can solve it by converting it to a logarithm and plugging it into your calculator. So now let's look at the properties of logarithms. And these properties of logarithms are a lot like the properties of exponents. If you think back, whenever we had two exponents multiplied together, what did we do? We added them. If we had two exponents that were divided, we subtracted them. So these are kind of the same. And we can go back and forth here. If we have log base b of two numbers multiplied together, x times y in this case, we can actually split those up, keep the base, and make it log base b of x plus log base b of y. And conversely, if we're given log base b of x plus log base b of y, we can do what's called condense that expression and put it back into log base b of x times y. Next, we have the quotient or subtraction rule. It depends on which way you're going. So log base b of x over y, or some number divided by another, is you take the log base b of the top number, the numerator, minus log base b of the denominator. And just the one thing I want you to make sure you notice here is that these bases are the same. The bases have to be the same in order for this to happen. Just like with exponents, with our laws of exponents, the bases had to be the same. Next is the power rule. And the power rule just says, well, if you've got something raised to a power inside your log, you can just take that power and just move it out front. So log base b of x to the fourth becomes 4 times log base b of the x. And again, conversely, if you're given 4 times the log base b of the x, or log base b of x, I'm sorry, you can take that 4 and move it up here. So just for a quick example, if I had log base 7 of x to the third, that would equal 3 times log base 7 of x. You just take that 3 and move it out front. All right, and next is our inverse properties. So if you're given either one of these, they are the inverse properties. I'll use black, let's use green. These are the inverse properties. And these are derived from function composition, where you take one function and plug it into the other. That's how we get our inverse properties. And this is just, you can think of this as canceling. So you got log base b of b to the x. Well, you think of these log base b's as canceling, and you're just left with x equals x. Same thing here. I have b raised to the power of log base b of x. Again, these b's cancel. You're left with x. Our next property is the same. It kind of goes along with our exponents. So remember when we had 2 to the x equals 2 to the y, then x equals y. If the bases are the same, our exponents are equal. Same thing here. If our bases are the same, which they are, b and b, then what we're taking the log of is equal. Next is our identity. Log base b of b equals 1. So anything, I take the log of anything of itself, it's going to equal 1. And then this up here is called the common log. If you look on your calculator, you just have log. That is actually log base 10. It's used so commonly that a lot of times you just get rid of the 10 and say just log. So if you just see log all by itself, that means log base 10. In the next video, I'm going to show you how to actually use these properties. It's going to be real quick. We're just going to do some condensing, some expanding, and then you'll see your homework.